Okay, welcome to 7.5 notes. Today we're going to be talking about greatest common factor as well as the zero product property, also known as GCF and ZPP. It's all about acronyms today. So the greatest common factor, this is probably something that you've heard before, but let's break down those words, right? Greatest is largest. Common means it's going to be in all of the terms of that expression. And factor, so the word factor means that it's multiplying. So we're looking for things that are in common, that are multiplying in all of the different terms in an expression. So what we're going to do is we're going to think about the prime factors of each number in that term. So that really kind of just means the smallest numbers. Like we can't think, like if we think about a number like 10, we could write 10 as 2 times 5. So 10 is not the smallest number because 2 and 5 are both prime numbers. So that's what we're looking for, numbers that we can't kind of break down into anything else, any other smaller factors. If each term has a variable, the smallest exponent will be how many they have in common, right? So if I say x squared, x to the third, and x to the fourth, right? This one has 2 x's, this one has 3 x's, and this one has 4 x's. They all have at least 2 x's. So you could factor out 2 of them. When we actually do our factoring, we're going to put the GCF on the outside of a pair of parentheses. And whatever's left over is going to go inside the parentheses in the same order, just like it should look like a distribution problem when we're done. So if we remove everything from a term, we just remember that that term becomes 1 because that is what we're actually multiplying by. We don't have to write times 1 because we could write times 1 a million times. It's not going to change anything. But if everything else comes out, we have to have that 1 there as like a placeholder. So here's our first example, right? We have 15x to the third plus 20x squared minus 25x. It's all stretched out just because I wanted to kind of group each term individually so you could see what's happening, right? So if I try to break down 15 into the smallest numbers that multiply to make 15, I'm going to get 3 times 5, right? 3 times 5 is 15. You guys can all agree with me that those are equivalent. X to the third means x times x times x. So x to the third and x times x times x are also equivalent. So 15x to the third we can write as 3 times 5 times x times x times x. So that's what we have here, right? We're just writing it down in all of its factors written out, just so we can look for what's in common, okay? Okay, looking at our second term, which is 20x squared, okay, we want to do the same thing. We want to break down 20 into its smallest factors. So you might immediately think 4 times 5, at least that's what I think of when I think of 20. But 4 we can actually break down into 2 times 2, because sometimes maybe we won't have a 4 in another number. Maybe we'll have like 6, right? 6 doesn't have, it's not a multiple of 4, but it is a multiple of 2. So that's how we get 2 times 2 times 5 down here as our factors. X squared is, of course, x times x, right? So that's 20x squared. This is equivalent to 20x squared. And then we have minus 25x. So you see the minus can kind of just hang out, right? It's just separating that 25x. But we don't need to worry about the signs too much, right? So we're just kind of looking for the factors and not caring about the signs at this point. So 25 is 5 times 5, right? Those are primes. So that's as much as we can factor 25. And we only have one x there, okay? So what we're going to do now is we're going to look at all 3 of our factors, or all 3 of our terms, right? And we're going to say, what do these have in common? So let's start with the number parts, right? 3 times 5, 2 times 2 times 5, 5 times 5. So maybe you said to yourself, I heard a 5 in every single one of those, right? So we're going to circle that 5. And then we're going to look at the variables separately. So we kind of do this in 2 parts. X to the third is x times x times x. X squared is x times x, and x is just x, right? So even we have 3, 2, and 1 x's, but they all have at least 1 x, and that's all we can take out, right? If I go to circle a second one, I'm going to be out of x's when I get to my third term. So we can only take out 1 x. So that stuff that we circled in each one, 5x, 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 That is our GCF, 5x. Okay, so that's what we put on the outside of parentheses. What's left over, so if I look back at what I have here, 3x squared times x, right? That's my first term. 2 times 2 times x is my second term. And then minus 5, that's my third term. So when I just shorten all that stuff up, right, 3x times x is 3x squared. 2 times 2 times x is 4x, and then minus 5. So here's my GCF, right? My GCF was the 5x that's out front, and then these are the leftovers that are inside the parentheses. Okay, let's do a few examples here just to practice. So if I look at my first example, A, we have 2n squared minus 6, right? So we want to kind of think about this as parts. So the first thing I do is I look at the numbers, the coefficients. 2 and 6. Can I think of a common factor? Sometimes we don't have to write them all out, but we absolutely can if we want to, right? So we might think to ourselves, well, 6 is 2 times 3. That's its prime factorization. So there's a 2 in common with 2 and 6, right? 2 and 6 are both multiples of 2. So I'm going to write 2, and then I'm going to look at my variables. Well, I have n squared in my first term, but I don't have any n's over here, right? So they don't have any variables in common. So I can't factor anything out that's a variable. So the only thing I can factor out is 2. So now another way to think about this is kind of think about dividing each of these by whatever you factored out. So if I factored out a 2, right, I'm just left with n squared in my first term, and 6 divided by 2 is 3. That was the other factor of 6. So I factored out the 2, and if I multiply this back together, I should get exactly what I started with because these should be equivalent statements. So for example B, it starts out very similar. We have 2n squared minus n, right? So now if I start with looking at my coefficients, I'm going to see 2, but I'm not going to see another coefficient, right? Which really means it's 1, but I can't really factor out a 1 because it's not really going to show, right? We're going to kind of ignore 1s when we're factoring. So I can't factor out any numbers, but I can factor out an n, right? N squared is n times itself, right? So this is really 2 times n minus n. So we have an n in both of these. So that's going to be my greatest common factor. And now I'm just going to think about what I have left over. So if I took out one of the n's, I'm going to have 1n left over. The 2 is still there, so we have 2n minus, right? And then what did we say we have? If everything factors out of our second term here, we have to put a 1 as a placeholder, right? Because if I multiply this back together, I need to multiply this times something to make that term. So we need to have something there or else it's not going to multiply back together correctly. So that is our answer. N is our GCF, 2n minus 1 is our leftovers. Our third example here, number C, is 3n to the third minus 12n squared. So starting with our coefficients, 3 and 12, can we think of a number that they are both multiples of, right? That's another way to think about this. So I think, well, 3 goes into 12, so 3 must be the greatest common factor. And then I look at my variables, n to the third and n squared, right? So the biggest exponent I see is going to be how many I can take out. If I have n to the third and n squared, that means I have 2 in common, two n's in common in both of them. And now we can think of this like a division problem, right? So if I divide by 3n squared, okay, in my first term, the 3's cancel because I've already factored out that 3. I'm factoring out 2 of the n's, leaving 1 n left over. And then my second term, 12 divided by 3 is 4, right? Think about multiplying it back. 3 times 4 is 12. So 12 divided by 3 is 4. It works both ways. And the n's are going to cancel because we factored out both of them. So that is our leftovers. Think about multiplying it back together and see how it becomes the exact same problem we started with. Okay, last example on this page. We have 3 terms this time. So remember, anything we factor out has to be in common in all 3 terms. So this might be where we want to start kind of writing stuff out a little bit more just to see what's in common here. So if I start with 10, 10 is 2 times 5, and we have x times x times x, right? X to the third. Plus 12, right? So I could think 4 times 3, but that's not going to match anything. So I'm going to think like 2 times 6 or 2 times 2 times 3, right? So I don't miss any of those prime factors. So there's my first term is 10x to the third. Second term is 12x squared. And my last term is 18, right? So 18, I think of 2 times 9, but 9 is really 3 times 3, right? So 2 times 3 times 3 times x. So there's my third term, right? And this might be where you want to kind of just pause, look at what they all have in common. You might also notice, hey, they're all even numbers, therefore they must have a 2 in common. So we know that they have a 2 in common. We can also look at our variables, x to the third, x squared, and x. That means they have 1 x in common. So each of these has a 2x, right? So we can think of dividing each of these by 2x. That's going to be our GCF. And then what do we have left over? Well, my first term, I have 5x squared plus sign. 2 times 3 times x, so 6x plus sign. 3 times 3, and that's it. 3 times 3 is 9. And that's it. There's our greatest common factor and what we have left over. So remember, if I multiply these back together, my first term is going to be 10x to the third. Yep. 2 times x, or 2 times x times 6 times x is 12x squared. Yep, that's my second one. And then 2x times 9 is 18x. So it works out. It multiplies back together. That's how we can check our work. Okay, let's do some more practice. We just got lots and lots of practice here today, just to get better at this. So again, the better we know our multiplication facts, the easier these are going to go. So like for number E here, I can see 12, 6, and 9. Well, 12 and 6 are both multiples of 6, but that doesn't work for 9. But I can think these are all multiples of 3. So if they jump out at you and you say, oh, these are all multiples of 3, right? You can even think 3 times 4, 3 times 2, 3 times 3, right? They all have a 3 in common. So that's going to be our greatest common factor. I see a squared, I see a, but 9 doesn't have any a's, so we don't have any variables in common to all terms. So divide each of these by a 3. So just kind of get rid of one of your factors of 3. So our first term is going to be 4a squared minus 2a plus 3, right? 12a squared minus 6a plus 9. It works out, so we know we're good. All right, our next one, 21b squared minus 7b. So hopefully we recognize that 21 is a multiple of 7. So I know that that's going to be one of my common factors. We also have b squared minus b, right? So b is going to be in both of those. So we can factor out 7b. So think about this. What multiplies to 21b squared? 7 times what makes 21? Well, 7 times 3 makes 21. B times what makes b squared? Well, b times b makes b squared. And that's kind of how you can backwards figure that out. And then 7b times what makes negative 7b? Well, here's where this whole thing came out, so we have to just put a 1 there as a placeholder. Okay, moving on to our next example, G, where we have c to the third plus c squared plus c. There's no coefficients here, so the only thing I have to look at are my variables. Well, they all have at least one c, right? So that's going to be my greatest common factor. We're going to think, well, if I had 3 and I take out 1, I'm going to have 2 left. And then for my next term, if I had 2 and I take out 1, I'm going to have 1 left. But then for my last term, remember, we need to have something here, right? C times what makes C? Well, it has to be our placeholder 1, okay? So there is going to be a 1 there. That's going to be the one number that, or the one term that ends up being a number, just because we took out the C, but it needs something to multiply by. So C times 1 makes C. So that's a tricky one right there. Okay, and for our last example here, before we move on to the zero product property, 12 and 18. Okay, think about that one, right? Let's think. Did you think of 2 because they're both even? Great. Did anyone think of 3 because they're both multiples of 3? Okay, well maybe if you thought both of those things, 2 times 3 is 6. These are actually both multiples of 6, right? So 12 is a multiple of 6 and 18 is a multiple of 6. That's going to be part of our greatest common factor. The next thing we have to look at is our variables. So x to the 5th and x to the 4th. One has 5, one has 4. They both have at least 4, right? We always look at the smaller exponent. And then we kind of divide out that GCF and see what we have left. So 12 divided by 6 is 2. X to the 5th divided by x to the 4th is x. Okay, second term, 18 divided by 6 is 3. And x to the 4th divided by x to the 4th, they're all canceled because they're already all factored out. So we are done. Okay, let's move on to the zero product property, also known as ZPP. So this is something that you guys have all known, right? If you multiply two numbers together and you get 0, one of those things has to be 0, right? Like if I said 2 times something equals 0, right? What do we know? We know that this has to be 0. Or if I said, let me just, if I said something times 6 equals 0, right? We know that that other thing has to be 0. So here's our shorthand, right? If I say two things that multiply, a times b, right? They just mean numbers. So if I multiply two numbers together and the product is 0, then what do we know? We know either a equals 0 or b equals 0. And what we're going to do is we're going to use this property to help us find, to help us solve equations. So we're going to use our factored form, which we just learned how to do, and then we're going to use this property of 0 to find what some numbers can be. So 0 is one of the special numbers because I know if I multiply to get 0, one of my factors has to be 0. So we want to make sure that our expression is written in factored form, right? That means parentheses. So multiplying two parentheses together, right? Or something like that. Multiply two things together to get 0. So we can call this guy A, this guy B. You might have to factor first. Set each factor equal to 0, right? Just like what we did up here. We said A equals 0 and B equals 0. And then we're going to have equations that we can solve. So here's the thing. We don't know how to solve quadratics yet, but we do know how to solve linear equations. So let's look at our first couple examples here, right? These are already factored, okay? This is factored form. I can tell because I have parentheses. I have two things being multiplied equal to 0. So think about if this is A and this is B, right? What do we know? We know that A equals 0 and B equals 0. So what I'm going to write is n minus 7 equals 0, right? That's my first factor, set equal to 0. I'm going to do the same thing with my second factor, n plus 1 equals 0. And now I can solve these two equations, right? So if I add 7 to both sides, I get n equals 7. That is one solution that makes this equation true. Same thing over here. If I subtract 1 from both sides, I get n equals -1. And there's my second solution that makes this equation true. Okay, let's look at our next example here. Here we actually have three factors. I have n, 2n plus 3, and n minus 5. So I'm going to set each of these equal to 0. So the first one is just n equals 0, right? Done. Solved already. The next one is 2n plus 3 equals 0. And my last one is n minus 5. Oops, that doesn't look very good. N minus 5 equals 0. And what we can do is we can solve each of these. So sometimes I have a no-step equation like n equals 0. Sometimes I have a one-step equation like n minus 5 equals 0, right? I just have to add 5 to both sides, and I get n equals 5. And sometimes I have a two-step equation. So let's look at this last one in the middle. If I subtract 3 from both sides, I get 2n equals -3. Divide by 2, divide by 2, and that's going to make this number right here negative. Oops, that doesn't look good either. -3/2 is my last solution. So -3/2. -3/2. -1.5. Same idea. But I had 1, 2, 3 solutions for that one. All right, so let's do some more practice here. So let's go to C, which says x plus 3 times 4x minus 1 equals 0. So remember, we have it factored, so we're going to set these equal to 0. Both of them, both sets of parentheses, both sets of factors. And we're going to solve these two equations. So this first one, if I subtract 3 on both sides, we're going to get x equals -3. The second one is a two-step equation, right? I'm going to add 1, get 4x equals 1, and then divide by 4 on both sides, and I get x equals this number right here, 1/4. Okay. Let's look below this. It says below is the graph of the equation y equals x plus 3 times 4x minus 1. So it's the exact same thing, but it's y equals instead of 0 equals. What do we notice? Well, look here. X equals -3 and x equals 1/4 are both special points on this graph, right? These are the x-intercepts. So they are where y is equal to 0. Interesting. Okay, moving on. Same idea over here. Here I have a three-factor equation, right? So I have x equals 0. That one's done. X minus 4 equals 0. So in this case, I just have to add 4 over to both sides. X equals 4. And then our last one, x plus 1 equals 0. Subtract 1 from both sides, and I get x equals -1. So look at these numbers that I got. 0, -1, and 4. And then we're going to look at this graph. Remember, this graph is the exact same thing, except it's y equals. Well, what do we notice? I see y-intercepts at -1, 0, and 4. Right? So this one's 4, 0. This one is 0, 0. And this one is -1, 0. -1, 0. Well, those correspond to our 3 solutions, right? So they are our x-intercepts. Cool. All right. And that's it. That is your notes for today. Just kidding. We have some factoring and then solving. So here's our last couple examples. So 4x squared plus 12x equals 0. So we're going to kind of ignore the equals 0 for right now. This is like something we just learned how to factor, okay? So we're just going to look at those first two terms, right, on the left side of the equal sign. And we're going to say, what do they have in common? Well, 4x squared plus 12x. 4 and x are both multiples of 4. And, oops, let's not do that yet. So 4 and 12 are both multiples of 4. X squared and x both contain at least one x, right? So we're going to put a 4x on the outside. We're going to say, what is missing? I need one more x for my first term, and I need a 3 to make a 12. 4 times 3 is 12 times x. Set this equal to 0, right? This is the rest of my equal sign. And now I can set my two factors equal to 0, just like we just learned with the zero product property. But here we're factoring and then setting these equal to 0. Okay, so the first one, 4 times x, I can divide by 4. That's going to give me x equals 0 divided by 4 is 0. And then x plus 3, I can subtract 3, which is going to give me x equals -3. So those are my two solutions for that one. We're going to do the same thing over here. We're just going to look at our two terms that are on the left side of the equal sign, 3x squared plus 18x. Well, 3 and 18 are both multiples of 3. So I'm going to factor out a 3. And we have x squared and x, so we both have an x. And then we think 3x times what makes 3x squared? I'm missing an x. 3x times what makes 18x? I'm missing a times 6. So 3x times 6 is 18x. Set these equal to 0. 3x equals 0. And x plus 6 equals 0. 3x, right, is x times 3, so I divide by 3. Nothing divided 3 ways is still nothing. And x plus 6, I have to subtract 6, so we get x equals -6. All right, now your notes are done for real. Thank you.